Hello, my name is Llana Abella, and I am an upcoming junior majoring in chemistry. I want to mentor for Chem 262, which is, as you know, organic chemistry too. The reason for that is I generally love chemistry, and I enjoyed Chem 262 with Professor Crimmins. I've also found that being an in class mentor or peer tutor for the Learning Center for these chemistry classes really helps solidify your understanding of these concepts. I mean, we've been told before that teaching is one of the best ways to master a subject. I mean, above all else, these topics make me excited about chemistry, and it's such a humbling experience to be part of the process where students, people my age, finally understand something that they may not have understood before.
Carboxylic acid derivatives and their reactivity. So, as you know, acid chlorides are more reactive than anhydrides, which are more reactive than esters, and esters are more reactive than amides. But before I explain this trend, I want to talk about why carboxylic acid derivatives are susceptible to nucleophilic attacks. And that's all about the partial positivity of this carbonyl carbon right here. So as you know, oxygen is a very electronegative atom. So what it's doing is it's pulling that electron density away from that carbonyl carbon, making this carbonyl carbon much more partial positive. And now a nucleophile can attack at that carbonyl carbon. And the reason that acid chlorides are more reactive than anhydrides, which are more reactive than esters, which are more reactive than amides, is because chlorine is an electronegative atom that's further pulling away that electron density from that carbonyl carbon, making it much more partial positive. And that's the same case with anhydrides. This oxygen right here is pulling that electron density from that carbonyl carbon, making it partial positive, and this carbonyl oxygen as well. But the reason that anhydrides are less reactive than acid chlorides is because anhydrides have this oxygen right here that has two lone pairs, which can donate the resonance electron density to this carbonyl carbon, making it less partial positive. And you might be thinking, chlorine also has lone pairs that can donate to this carbonyl carbon, making it less partial positive. But if you look at the periodic table, you have carbon right here, nitrogen, oxygen, and then fluorine, neon, and then right under fluorine you have chlorine. You see that carbon is in a 2p orbital and chlorine is in a 3p orbital. So this 2p 3p orbital interaction makes it less makes resonance and the donating of electrons less prominent than if it were the carbon oxygen bond, which is in a 2p orbital interaction. Now, anhydrides are more reactive than esters is because you have this group right here that's further pulling away electron density, whereas with esters, you only have a carbon bonded to that oxygen. Again, you have the lone pairs that's donating electrons, and this electronegative oxygen pulling away electron density, making this partial positive. And esters are more reactive than amides because, again, if you look at the periodic table, nitrogen is less electronegative than oxygen, and it has a lone pair which can donate the resonance again. But since nitrogen is less electronegative than oxygen, it's better at donating those electrons than oxygen would, and nitrogen is a better resonance donor. And since it's a better resonance donor, it's making the partial positive charge of this carbonyl carbon less than if it were an oxygen.